So it spans a lot of different things. So Stinger is a nice way to sum that up. What I want to be clear about here is people ask me all the time, is Stinger your SQL product? No, Hive is our SQL product, right? That's not changing. Stinger's just the initiative to make that better. So, small plug for the Hadoop Summit. It's wonderful. There's lots of great programs. I happen to be on one program committee, so I can say with authority there's lots of great talks coming. All right, so back to Stinger. What is the goal of Stinger? As a lot of people have noticed, Hive doesn't do everything you want it to do today, right? So what are the things people want Hive to do? One is they want it to go faster, right? Right now, you start a Hive query, you go get a cup of coffee, you go play ping pong, whatever it is you want to do, then you come back and you get your results, right? And that's not cool. So one of the main goals of Stinger is to drive Hive to the point where it responds to what we call human time. So that doesn't mean sub-second. That doesn't mean something you can hook up to a front-end service system. That's not the goal. But it is the goal that a human sitting there at the terminal can type queries and get back results in 5 to 30 seconds. It's something that's going to be reasonable for an interactive session. Right? You don't want to be typing queries and then time splicing off to something else and coming back and flipping back to that page and saying, oh, did I get a result? Okay, go do something else again. So that's one of the goals. But that's not the only goal. The other goal is we need Hive to do the things people want. Right? We go out and talk to Hive users, which we do a lot now in our business. We also hear that it doesn't have the SQL features people want. People want to do analytics with Hive. They want to hook it up to their BI tools. They want their analysts that are already SQL users, Power SQL users, to be able to use it and have the features they expect. So that's the other half of the Stinger initiative. This isn't just about making it faster, it's also about making it be the right tool for doing analytics on top of Hadoop. So we'll walk through some of that tonight. So first thing, let's talk about some near-term performance changes. Turns out that there's a fair amount of low-hanging fruit in making Hive go faster. When we sat down and started looking at this several months ago, it became obvious there was a lot we could do very quickly to make this better. And so here's some of the things that work has been going on in Hive to make better. One thing I want to stress here is, I work for Hortonworks, these slides are from Hortonworks, but that doesn't mean all this code is from Hortonworks, right? This is the Hive community. We're seeing contributions from Hortonworks, from Facebook, from SAP, from others, all over the Hive community, helping add this code. So this is very much a community effort. I just want to be clear. I'm not trying to grab the credit for somebody else's code. So some of the things that have been going on. One, people want to do star joins, right? For a long time, users have been trained to take their data and put it in the data warehouse in the form of a star schema. Well, it turns out star schemas were really poorly in Hadoop because that means denormalizing everything, and that means doing a whole bunch of noise. And that's what Hadoop doesn't do very well, right? But when you tell users that, you say, well, just denormalize all your data, that doesn't actually work either, because it turns out that all their other systems do work really well with that. So they end up spending a lot of time pulling their data into Hadoop, denormalizing it, doing a few Hadoop things, and then renormalizing it and shut it back out. Right? I've seen workflows where people are spending 75% of their time translating between normalized and denormalized just so they can make the data flow back and forth between Hadoop and whatever other systems they're using. That's not really cool. Right? So we need to make star joins work in Hadoop. So a lot of work has gone on recently in making those kind of joins work in Hadoop, and I'll show you an example of that here in just a minute. The second bullet point here is there's a lot of places today where Hive just doesn't take advantage of things. A lot of places where there are adjacent MapReduce jobs or map-only jobs followed by MapReduce job that you can push together. An example of that is if you have a group by followed by an order by in your query and they're on the same key, today Hive will still run those as two separate jobs, even though after that group by it's going to reshuffle that data and the partitioning is going to end up exactly the same as it was. It doesn't realize that, it doesn't take advantage of it. And there's a number of places where that's true. So there's been a lot of work going on to change that and to make it so that the optimizers are smart enough to realize, oh, I can combine these two MapReduce jobs, or I can get rid of this job altogether. So let's, slides are nice, but results are better. So let's look a little bit at some early results we've seen. This is done against what is now the Hive 011 branch. So this is, well, mostly, I'll walk that back in a second. But the code in Hive here is from the Hive 011 branch. It is run on top of Yarn with the new test stuff. So these numbers would look slightly different if you ran it on Hadoop 1, but not that much. So on the far left here we have Hive 010. This far left blue column here is Hive 010 with the data stored as text. Let me talk a little bit about the data we use. This is from the TPCES benchmark. That's a decision support benchmark put out by the TPC guys. And query 27 is a very classic analytics type query. It's a four-way a star join with four-dimension tables, one fact table, followed by group by and order by, with group by and order by are on the same key. Okay? Very simple query. So on the left here, you see that done with text. Oh, it's scaled to 100 means the whole data set is 200 gigs. So this query is actually scanning around 80 gigs, I believe it is. So if you put everything in text and you do it, this is the number you get, 1,500 seconds. And the reason we put that up there is just, frankly, when people want to use Hive as a punching bag, which they often like to do when they post their, look at how much faster we are than Hive for their latest product. This is what they tend to do. They put it in text files, and then they go, yeah, we're faster than Hive. Well, okay, so there's a lot you can do without even getting to that, right? If you move it to RC file over here, the red bar, you get 1,100. If you move it to RC file and you partition it by date, you get 631. So now we're kind of bumping up against the best you can do in Hive 010 with this data set. That's the yellow or green bar there. Once you take the optimizations that I talked about that are in Hive 011 and put them there, you get in the under 1 minute range. So we haven't even started on some of the more advanced, cool optimizations we want to do that we'll be talking about here a little bit. And we've already made some very significant progress on performance. So just to show that that's not the only changes we've been making, one other query that we have been working against was query 2, which is a fact-to-fact join. So this is one where you can't cheat by fitting one of the tables in memory. And we're still seeing some very nice speed ups here. We're not under the minute range yet here where we want to be, but we're still speeding up pretty nicely. So let me talk quickly about how we did some of that, and then I'll move on to features. So this is what the query 27, the first graph I showed you, this is what Hive's plan looked like in Hive 010. So there's 6 MapReduce jobs, one for each of the joins. So in job 1 up there, it takes the fact table and the first dimension table and does it, and then moves along slowly for each of the joins, finally does a group by, and then does an order by on the same columns, right? So 6 separate jobs. That's where that 600 second number is coming from. With the changes that have gone in so far, we make start joins work well. So what is that change? The basic change there is making it so that you can load all the dimension tables in memory on every map and run it as a map only job, right? So I could already do that, but it would do it one table at a time. Now it can do that for multiple tables. And the other nice feature is in cases where they don't all fit, it can figure that out, and it can do one job with as many tables loaded as it can, and then turn around and do another job with as many loaded as it can. So it's going to optimize that query to be the best it can at doing those joins in memory. And then it goes ahead and does the group by via the shuffle and the reducer. And finally, it doesn't even need to order because the order and group are on the same key, moving it up. So that's how we're pushing it from 600 seconds to 40 there. And that just those changes. All right, I want to change gears now and talk a little bit about features. I said that people don't just want it faster, they want it to have new cool features. So one of the things that we hear people asking for, and that there's been a lot of interest in the community in adding, is windowing and analytics functions. This work was actually started at SVP and pushed forward mostly by them, but lately some other people in the community, including us at Hortonworks, came alongside that and started helping out. And so this is actually all checked in. It's even in the trunk now. So over clauses with the existing aggregate functions plus all these new windowing and analytics functions that are listed up there are now in there, including you can do multiple over clauses in a single Hive query. So this is very nice, a feature that we think will open up analytic or use of Hive to a lot of people who want to do rank and flow number and those kinds of things. All right, some more analytics work. Queue by rollup already been added to Hive. That went in 0.10. You see a lot of people say they'd like to do subqueries. So there's plans to start work on adding subqueries in the where clause. Hive can already use subqueries in the front clause, right? But we'd like to be able to do it in the where clause. With plans to start work on that soon. This will not be a Hive relevant. The first pass is we plan to support in and not in for non-correlated subqueries only. Doing correlated subqueries along the work. And then finally, we want to add new data types. A big issue that a lot of people encounter when they try to connect Hive to their systems or just give it to analysts who are used to SQL. Hive has a Java type model, right? It thinks in string, int, float, that kind of stuff. And when you give this to a SQL power user, they think in varchar and datetime and all these things that Hive doesn't have. And this is particularly problematic when you go to connect Hive to other systems that are working with relational data, right? Because you connect this to a relational database, and Hive says, this column is a string. The database says, what's the limit of the size of that string? And Hive says, I don't know, it's a string, right? So we need to add the data types in that SQL users are used to. Obviously, you can't get rid of the existing time model, you wouldn't want to if you could. But we need to add in datetime, we need to add varchar, we need to add options to use precision and scale for types like decimal and float that are already there, but currently are unbounded. Or actually, well, unbounded isn't quite fair. Have a fixed bound that you can't change. All right, we're done.
Okay, I'm Owen. And one of the things that we realized when we started working on Hive was that it has a built-in file format called RC file that stores your columns together. But we wanted to make some improvements for it. The first, most critical thing, well, actually there were two main thrusts. The first is we wanted to get smaller data sizes. And the second one was we wanted to increase the speed that you were able to do queries against these files. And so the first one that we wanted to address was getting the size down. And in order to do that, we wanted to take a very different approach from, say, RC file or sequence file, which treats each of the values as a binary blob. RC file will separate by columns, but each column is just a set of bytes, and it doesn't know what the types are. So we wanted to be able to take a very different approach and have type-specific encoders for each type. So you wanted to be able to say, okay, this is an integer column. I want 0 to take less bytes than 5 million. I want long runs of numbers to be running encoded. I want this very kind of specific kind of knowledge baked into the file format so that it can make the file smaller before you even get to gzip or LVO. So we had a couple of other constraints. The first is that Hive does much better files rather than multiple files. There are a lot of reasons for that. Most of them we should fix in the long term, but in the short term, it made it easier. It's a single file for your logical file. It also has this added benefit of lowering the pressure on the main node, because if you create 5 files for every file you create, it means that you've got 5 times the number of files in your main node that has to be tracked of. We needed to support all of the Hive types, of course. We needed to support structs, maps, lists, unions, and all the primitive types that are there. One of the issues with RC file that we've seen that impacts the performance is that when MapReduce wants to work on a chunk of the file, it has to scan a starting point and start walking through, looking at it byte by byte, trying to find where the next set of rows started. We didn't want to have that scan, so we keep an index for where each set of rows start at the bottom of the file. And finally, we need to be able to bound how much memory we use when we're reading or writing, because tasks don't have an infinite amount of space. So to get there, we divide the file into logical regions called stripes. Stripes contain a whole set of groups. They default to 256 MB. And that large size is because you may just be reading some of the columns out of the file. And if you have 4 MB, which is what our RC file has, then if you've got 100 columns, each of those columns is only 40K. That's a very small B for a normal file system and a tiny B for HDFS. If you've got 256 MB for the size of your stripe, then you're reading 2 meg for each of those columns, so you get much better throughput. We also have a footer that describes the types that are in the file, so that you can read the file without knowing what types were there when you wrote it. We also keep some metadata. Now, metadata is pretty small, but we keep the min and max of each field, how many values we had for each column, and the sum of those. And that will enable us going forward to be able to do much faster versions of counting how many rows there are in a file. And finally, that footer itself can be compressed, so we need to record how it's compressed at the very tail of the postscript. So what do stripes look like? They have 3 main pieces. The main piece, of course, is the primary data. The data is the data that will be required for the scanning through. We also have a very lightweight index. The index is so that you can jump to a particular row number. That lets you support secondary indexes. But more importantly, we also include in that index the minimum and maximum values for each of the columns. Because we have those, we can push down the predicates into the reader, saying, okay, I'm only interested in records that are in California. That means if the minimum state is Nevada and the maximum is New Mexico, you're not going to have to read those 10,000 rows at all. You're going to skip over without reading the bytes. That's a huge win. We currently have the indexes in with just min and max. We could add a little filter, but that's coming. And finally, at the bottom of the stripe is a footer that describes where the parts inside the file are. This is what it looks like. So here you've got a file with 3 stripes. The index data is at the top, broken down by column. The blue section is the row data. It's also broken down by column. You do this, of course, so that if you are just reading columns 1, 5, and 6, you can just read the bytes that you need. And then the stripe footer is at the bottom. And down at the very bottom is the file footer postscript. Okay, so how do we actually encode the integers, right? I said that there's strong-length encoding. So how do we actually encode it? And the answer is that every set of integers starts with a byte that says either this is run-length encoded or it's a bunch of literals. If it's a run, then we start with what value it is and how many instances it has. And actually, we can even do a little bit better than that. we can say how much each instance is bigger than the one before. So if you've got a fixed delta between your thing, you can encode it as a run. That helps a lot for ID values. If they're literals, actually even if they're runs, we encode everything using variable width encoding, so that if you have 0, it's just encoded as 0. 1 is also a byte, but 5 million will be the number of bytes. The variable width encoding we use is based on one protocol buffers. Okay, now one of the things that we noticed in reading the research papers there also is that often we've got low cardinality columns for strings. You have something like a state where there's only 50 values, but you still have a couple of bytes for each of those strings, and that's a waste. And so what work does is it keeps a dictionary of the values you've seen for that column, and then the data consists of an index into that dictionary, so that you'll have each state once, and then you'll just have an integer from 0 to 49 indexing into that index. Now, of course, that's not always, you don't always have a low cardinality string column. And so the guys at Facebook just put in a nice feature where it looks at the first 10,000 value or 100,000 values of that column and decides whether to do a direct encoding or to do a dictionary encoding based on how much duplication there's. That means that you can let it choose for you, and it'll dictionary encoding or direct encoding depending on which one's better. We also sort the dictionaries. That'll help optimize things later, because when you're looking for a particular value, you can look it up in the dictionary using a binary search, and then scan the list of integers looking for a particular integer. So you're just doing an integer compare rather than a string compare. Compression. Of course, we get all this lightning compression for free all the time, and that actually gets it down reasonably small. But then you can also throw zlib or LZL on top, and that will shrink your files even further. The compression on top means that it's done in blocks rather than streams, because we want to be able to seek to inside of a compression stream. So we need to know, okay, if we seek to this part, we start decompressing and skip over this many uncompressed bytes, we can jump into the compressed stream. That's actually really important, so that you don't have a whole too big byte chunk that you need to decompress to get the byte down to the bottom. The compression is also done incrementally, so that as it's storing up the buffer, and when you're writing it, it stores it compressed rather than waiting until everything is ready and then compressing it, which is what our C file is. Of course, one of the critical features is that it honors the calls that are used in your query. It will only read the bytes that are necessary. That's in there now. The filter pushdown, which is using the index to skip over pieces, isn't going to be in the first version. Because I do this at work, it's already checked into from which one you come. I have 11. So it'll be there. The predicate filtering isn't done yet, so that will have to go to 12. Okay, now looking at the sample sizes, these are the ones from DPCDS. So I've normalized the text form of the files at 1. You can see the RC file came down to roughly 60% on these. Oh, sorry, Red and Blue are two different files out of that benchmark. Orc, on the other hand, comes down to roughly 20%, even before you turn on compression. Then you start turning on compression. The gzip version of the files is about the same size as the orc file without compression. RC file with the zlib is smaller, and then the orc and the zlib is small instead. And yeah, that little line is actually still there, it's just so small you can't see it. Well, your results won't be that good. Generally, data, so compressed really well. All of the metadata in ORC is encoded in protocol buffer so that we can add and remove fields as we need. Like I said, we can seek to an individual row so that if you make an index on top of ORC, you can seek to the row efficiently. Unlike a lot of parts of Hive actually worry about concurrency, and so you can actually have multiple row meters running at the same time. And it doesn't, I guess that's one limitation that I'll probably need to fix, but HDFS currently does checksums all the time. You can't turn it off. And so I didn't put checksums into the work. It would be easy to add those later. And at some point, the writer may reorder rows to improve the compression. Here's a comparison of RC file preventing, which is another file format that's part of Avro. Okay, now Tez. Tez is a new project that we started in the Apache incubator. As Alan said, we put all of our code back into Apache. So Tez is actually at an incubator. And it came out of the realization that MapReduce isn't a very good match for a lot of SQL queries. You can make the SQL query processing fit into MapReduce, but it's not a very natural fit. And so we wanted to say, okay, what do we want the execution model to be? And rather than throw out all of MapReduce, we decided to base it on Yarn and generalize it from there. Of course, it'll remove the tasking job launch times. We'll have Hive depend on Tez MapReduce, and we'll be able to pull out the intermediate writes to HDFS so that you can just use a set of shuffle, the equivalence of shuffle where you write the local disk instead of HDFS. And everything will be built on Yarn. Okay, so what does it look like? Fundamentally, Tez takes MapReduce and generalizes it into libraries that are components that you can plug together. So you can think of MapReduce as a particular construct, and Tez takes the pieces and makes them into building components that you can put together however you need to. So you've got a processor and input and output. And from that, you can assemble DAGs or whatever you need. Now, we expect mostly frameworks to use Tez, but of course it'll be available for application mostly. I'm running out of time. Okay, so one of the first pieces is MapReduce has an input for the map, and then the shuffle output. The MapReduce reduce has a shuffle input and an HDFS output. And so normally you put those two pieces together. Well, one of the natural intentions is to say, okay, well, what if I want to do a second shuffle so that I shuffle again on a different key? So that pattern is called MapReduce reduce, and with Tez, you can just say, okay, I want one of the map Lego pieces, I want one of the reduced pieces, and then I want a second reduced piece, so that it shuffles on something else, so that I can take MapReduce and extend it to do new things. Of course, we also pick up the ability to define more tasks and more different kinds of shuffle. So here's one of the examples. On the left, you have what currently happens in the MapReduce, where you've got